Good day, class. Today we will discuss the real start of Module 2, which is Lecture 5A, Principles of Volumetric Analysis. Recall that a volumetric analysis is a quantitative chemical analysis wherein the amount of a substance is determined by relating it to the volume of a second substance that reacts with it. This is also called titrimetric analysis. In this lecture, you will be able to learn the different requirements of titration. You'll also learn the different qualities of a primary standard and be able to differentiate it with a secondary standard. Third, you'll be able to express concentrations in molarity and normality and then use them in titration problems. And then finally, you'll be able to learn how to calculate back titration problems. So let's start with what is titration. It is an analytical technique wherein a standard solution, which we call the titrant, is added to the analyte until the reaction is judged to be complete. In this lecture, we will focus our discussion on volumetric titration, which is so called because we determine the amount of analyte based on the volume of the standard solution that was added. From your virtual experiments and discussions in the lab, you have learned the general methods for titration. Basically, a titrant of known concentration is carefully added to the solution that contains the analyte. The consumed volume of the titrant is then used to calculate the amount of analyte in the solution. For the titration analysis to be successful, it must meet several requirements. First, the reaction should have a known and definite stoichiometry. This will give us a way to calculate the amount of substances involved in the titration reaction through stoichiometric relationships. Second, the reaction should be fast so that we can be sure that the titrant species are reacting with the analyte. If a slow reaction occurs, then a higher amount of titrant may be added to the analyte, resulting to incorrect calculations. Third, the reaction should be complete. This means that all, or at least 99.9% of the analyte have reacted with the titrant to be able to calculate the accurate concentration of the analyte. And finally, there must be a clear change in some measurable property which signals that the reaction is complete. As you may already know, the occurrence of this clear change is called the endpoint of the reaction. Now let us define some terminologies used in titration. First, indicators. Indicators may be visual or instrumental. Visual indicators are substances added to the analyte solution which may participate in the titration reaction so as to give a clear visual change at or near the equivalence point. Instrumental indicators, on the other hand, are those that use analytical equipment to detect changes in characteristics of the solution as the reaction proceeds. Example of this is the potentiometric titration, which analyzes the change in pH to determine the equivalence point. Next, equivalence point. This is the point wherein the titrant is added in enough or stoichiometric amount to completely react with the analyte solution. This is considered as the theoretical endpoint. Next is the endpoint. The endpoint is signaled when a physical change is already visible in the reaction. If the experiment is properly designed, the endpoint can be considered a close approximation of the equivalence point. Next, titration error. The titration error may be calculated by getting the difference in titrant volume of the endpoint and the equivalence point. Next is blank titration. If the solution contains other reactive amounts other than the analyte, a blank titration is done to determine the errors contributed by such conditions. A blank titration is performed the same way as the main titration, but without the analyte. The volume of titrant used in blank titration is then subtracted from the volume consumed in the main titration so that errors may be eliminated. Next, back titration. This is also called indirect titration. This is generally a two-step analytical technique wherein the analyte B is first reacted with excess amount of the titrant A with known concentration. Then, the amount of the excess titrant A is determined through direct titration using a different substance as the titrant. Back titration is usually done when the reaction is too slow or when the titrant is unstable, for example, ammonia which is volatile, or if the endpoint is difficult to observe, which is the case for weak acid, weak base titration reactions. Now we go to standard solutions. This is a reagent with a precisely known concentration. In titration experiments, this is commonly used as the titrant. There are two ways to prepare standard solutions. First is the direct method, wherein a precisely measured amount of the primary standard is dissolved in a suitable solvent and diluted to a known volume in a volumetric flask. The concentration is then calculated from these known values. Second is through standardization. The concentration of the standard solution is determined by using it to titrate an analyte with a precisely known amount. Stoichiometric calculation is then done to obtain the concentration. Standard solutions must possess certain characteristics to make it ideal for use in titration experiments. First, it must be stable. This means that its concentration must not change over time to avoid the need of repeating the standardization process. In addition, the standard solution must react rapidly, completely, and selectively with the analyte. These characteristics will promote the effective and accurate determination of the amount of analyte through titration. Standard solutions can be classified as primary or secondary standards. A primary standard is a substance with known concentration that is used as a reference chemical to determine the unknown concentration of a different substance. Certain properties must be possessed by the primary standards. It should have high purity, stability, and solubility, and it should not contain hydrates. These factors can alter the reaction stoichiometry of the standard and the analyte. It is also preferred that primary standards have high molar mass for more accurate weighing. And finally, for practical reasons, it should not be expensive and highly available. Substances that do not meet these criteria are called secondary standards. The concentration of the secondary standard is determined by titration with a primary standard analyte. For example, NaOH or sodium hydroxide is considered a secondary standard because, as discussed already in your laboratory class, it is unstable in air due to its deliquescent property and reaction with the carbon dioxide in air. The concentration of NaOH is usually determined by titration against a primary standard solution of KHP. Shown in this table are some examples of primary standards used in different titration reactions. As seen in the previous slide, there are several types of volumetric titration according to the nature of its reaction. We have acid-base or neutralization titration, precipitation titration, complexometric titration, and redox titration. These types will be further discussed in the succeeding topics of Lecture 5, but let's introduce them briefly here. Acid-base reactions are performed with standard solutions of either strong acid or strong base. The main reaction is neutralization, which is mainly characterized by the rapid change in pH. In that regard, the endpoint is detected by using an acid-base indicator which changes color at a particular pH. We could also determine the endpoint by monitoring the change in pH with the addition of the titrant. This technique is called potentiometric titration, which uses an instrumental indicator. Precipitation titrations are those that form an insoluble compound or precipitate with the reaction of the titrant and analyte. The most common precipitation titration are the argentometric titrations, which use silver ion or Ag+ as the precipitating agent. The endpoint is detected experimentally when the silver ion reacts with the indicator to form a differently colored solution or precipitate. Complexometric or chelatometric titrations are governed by complex formation reactions between a metal ion and a ligand from a complexing agent. This is usually done to detect metal concentrations in the solution. A primary standard commonly used for this type of titration is ethylene diamine tetraacetic acid or EDTA. Finally, we have redox titration, which is usually applied for elements with more than one oxidation states and undergoes reduction-oxidation reactions. Now we move on to titrimetric calculations. First, it is important to recall these equations for mole, millimole, molarity, and dilution, which will be very useful in the succeeding calculations. These have been repeatedly discussed before, so we will no longer focus on this too much. As discussed in Lecture 2, concentrations can be expressed in several ways. For titration calculations, it is more common to express concentrations using molarity and normality. First, let's discuss calculations using molarity. When we use molarity, calculations are mole-based, and thus stoichiometric relationships are important to be known. This means that the balanced reaction must be defined because the equivalence point is based on when the analyte and titrant are in their stoichiometric amounts. Let's consider this neutralization reaction. Let's say we want to determine the concentration of the acidic analyte by titrating it to completion or to the equivalence point with the basic titrant. To do that, the moles of the base is related to the moles of the acid using the stoichiometric ratio of the acid and the base. Since you are already familiar with stoichiometric calculations, let us proceed to the sample problems. For the first sample problem, a given sample containing sodium carbonate requires 26.2 ml of 0.1 molar hydrochloric acid for titration according to this reaction. Calculate the weight in milligrams of sodium carbonate. You may pause this video if you wish to solve this problem first on your own. I have already highlighted here the givens and the required. The balanced reaction is also provided. To solve this problem, first get the moles of HCl and then multiply it by the stoichiometric ratio to get the moles of sodium carbonate. And then finally, convert it to mass using the molecular weight. Let's see our resulting equation. The moles of HCl is obtained by multiplying the given concentration of 0.1 by the volume used, which is 26.2 ml. The stoichiometric ratio is based on the chemical equation where 2 millimoles of HCl reacts with 1 millimole of sodium carbonate. And then finally, to convert the millimoles of sodium carbonate to mass, multiply it by its molecular weight. Calculating, we get 138.85 milligrams. Now, let's work on this second problem. Exactly 410.4 milligrams of primary standard potassium acid phthalate is weighed out and dissolved in water. If titrating the KHP requires 36.7 ml of sodium hydroxide solution, what is the molarity of sodium hydroxide? The reaction of sodium hydroxide and KHP is given as such. So if you want to solve this problem first on your own, you may pause this video. So I have highlighted the givens and the required for this problem. So to solve this, first, get the moles of KHP by dividing the given mass of 410.4 milligrams by its molecular weight of 204.2 milligrams per millimole. And then, multiply this by the stoichiometric ratio, which is 1:1, to get the millimoles of NaOH. And then finally, divide by the given volume of NaOH, which is 36.7 ml, to get the required concentration of sodium hydroxide, which is 0.055 molar. Another way to express concentration in titration calculations is by using normality. Normality is a concentration that is based on the number of equivalents instead of moles. This is more convenient to use than molarity if you don't know the stoichiometric relationship of the analyte and the titrant, because at the equivalence point, the number of equivalents of the analyte and the titrant is always equal. Again, when using molarity, the stoichiometric ratio depends on the balanced reaction. For normality, the equivalence ratio of the reactants is always 1:1. Normality is calculated by the number of equivalents over the volume. It has units of equivalents per liter or milliequivalents per milliliter. The number of equivalents is calculated from the mass of the substance divided by its equivalent weight. And the equivalent weight is defined as the molecular weight of the substance divided by the equivalents per mole factor N. The determination of this factor will be further discussed in the succeeding slides, but generally, its value is dependent on the type of reaction and the reactant used in titration. Now, if we substitute the equations for the number of equivalents and equivalent weight in the equation for normality, we can get an equation that can be solved from known parameters of the reaction. If we want to get an equation in terms of volume instead of mass, we first recall that for calculations based on normality, the number of equivalents of the analyte is always equal to the reacting equivalents of the titrant at equivalence point. We know from the previous slide that the number of equivalents is mass over the equivalent weight. And then recall that equivalent weight is equal to the molecular weight divided by the equivalents per mole factor. Now, from the definition of normality, we can say that the number of equivalents is also equal to the normality concentration multiplied by the volume. So, taking this relationship or this equation and isolating the mass of the analyte, we get this equation. This is another equation that can be solved from parameters that are usually known from experiment information. Another important equation for normality calculations is the relationship of titrant and analyte equivalents. We have already mentioned a number of times that at the equivalence point, the equivalents of the analyte and titrant are just equal. From the previous slides, we know that we can get the number of equivalents by multiplying the normality with the volume of the substance. So substituting that, we get this equation. This is similar in form as your dilution equation, which I guess makes it easier to remember. Another equation that is very useful is the relationship of molarity and normality. If you wish to convert from molarity to normality, you only need to multiply the molar concentration by the equivalents per mole factor N. Now, how do we get the equivalent per mole factor N of a substance? This parameter is defined as the number of reacting units that is supplied or received per mole of a substance. Determining the value of factor N depends on what type of reaction there is. For acid-base reactions, the factor N is equal to the number of H plus or OH minus transferred by an acid or base respectively. For example, the factor N for sulfuric acid is 2 because it has two H plus ions that can be transferred in the reaction, while the base sodium hydroxide has a factor of 1. For precipitation reactions, The factor N is equal to the absolute value of the charge of the cation or an ion participating in the reaction. Example, in the precipitation of lead iodide, the lead ion has an equivalent factor equal to 2, while iodine has N equal to 1. The equivalence per mole factor for complexometric reactions depends on the number of electron pairs that the metal ion accepts or the ligand donates. In the complex formation of diamine silver ion, the equivalent factor of silver is 2 since it accepts 2 ammonia, while one ammonia molecule has an equivalent factor of 1 since it can only donate 1 electron pair. And for redox reactions, the factor N is generally determined by the number of electrons a substance can transfer. For example, in the given redox reaction of iron and tin, iron accepts 1 electron while tin donates 2 electrons. However, there are substances that react differently when the condition of the reaction is varied. Take for example the compound potassium permanganate. In basic medium, permanganate accepts 1 electron to form the manganate ion. But if it is in acidic medium, it reacts differently by accepting 5 electrons to form the manganese ion. And when it is at neutral condition, it accepts 3 electrons to form the manganese oxide precipitate. Because of this, the value of the equivalent factor, which is equal to the number of electrons transferred, also varies. So for substances similar to this, it is important to identify first what reaction it undergoes before being able to determine the value for factor N. Now let's check your understanding of the normality calculations by answering this problem. A hydrochloric acid solution is standardized by titration with standard sodium hydroxide. If 25 ml of HCl requires 32.2 ml of 0.095 normal NaOH for titration, what is the normality of the HCl solution? Since the concentration and volume of the titrant NaOH are given as well as the concentration of the analyte HCl, we can use this equation to solve for the concentration of HCl in normality units. Substituting the givens and calculating, we get 0.122 for normal HCl. For the next problem, a 150 mg sample of pure sodium carbonate requires 30.06 ml of hydrochloric acid solution for titration. Their reaction is given as such. Calculate the normality of hydrochloric acid. To solve this problem, we use the definition of normality, which is equivalence per volume of HCl. To get the equivalence of HCl, first, get the millimoles of sodium carbonate by dividing the given mass by its molecular weight. Next, convert the millimoles of sodium carbonate to milliequivalents by multiplying it by its equivalence per mole factor. Since carbonate can receive 2 protons, its factor N is equal to 2 milliequivalents per millimole. Then, multiply this by the 1:1 equivalent ratio of HCl and sodium carbonate to get the milliequivalents of HCl. Finally, divide this by the volume of HCl used, which is 30.06 ml, to get the normality of HCl equal to 0.094 normal. We can also solve this problem using molarity calculations and then just convert the obtained molar concentration of HCl to normality using the relationship normality is equal to the factor N times molarity. So to solve for the molar concentration of HCl, first, we must determine the millimoles of sodium carbonate by dividing the given mass of the sample by the molar mass of sodium carbonate. Then, we multiply this by the stoichiometric ratio of 2 millimoles HCl is to 1 millimole of sodium carbonate. Once we have the millimoles of HCl, we divide that by the volume of HCl used to obtain 0.094 molar. We convert this to normality by multiplying it by the factor n. Since HCl only has one H+, then the factor n is just equal to 1. Solving, we get 0.094 normal, which is just the same as the previous solution. Now let's go to calculations involving back titrations. Recall that the back titration involves a two-stage method. First, the analyte is reacted with an excess titrant A. Then the moles of the excess substance A is determined by a second titration using another titrant, substance C. Substance C reacts only with the excess substance A. To get the actual moles of A that reacted with the analyte, we get the difference of the total moles of A added and the moles of A that reacted during back titration reaction. If you want to get the mass of the analyte, multiply the moles of the titrant that reacted with the analyte by the stoichiometric ratio of the analyte and titrant, and then convert to mass by multiplying it with the molecular weight. To understand better, let's consider this problem. A 0.4755 grams of sample containing ammonium oxalate and inert materials was dissolved in water and treated with KOH, converting ammonium ions to ammonia. Exactly 50 ml of 0.05035 molar sulfuric acid was added to react with ammonia. The excess sulfuric acid was back titrated with 11.13 ml of 0.1214 molar NaOH. Calculate the percent ammonium oxalate in the sample. If you wish to solve this problem first on your own, you may pause this video now. Since we will be solving this problem using molarity concentrations, it is important to determine first the balanced equation for the main titration reaction and the back titration reaction. In the first stage, ammonia is reacted with excess sulfuric acid. Then, in the back titration, the excess sulfuric acid is reacted with sodium hydroxide. To solve this, first we must determine the moles of sulfuric acid that reacted with the analyte ammonia. We can get that by subtracting the excess moles of sulfuric acid from the total moles of sulfuric acid initially added. The total moles of sulfuric acid is obtained by multiplying the given concentration by the volume added. Do not forget to convert the given volume to liters. Then, the excess moles of sulfuric acid is determined from the back titration reaction and is calculated by getting the moles of NaOH reacted and multiplying it by the stoichiometric ratio. Calculating, we get 1.832 times 10 to the negative 3 moles of sulfuric acid that reacted with ammonia. The percent ammonium oxalate is determined using this equation. To get the mass of ammonium oxalate in the sample, multiply the moles of sulfuric acid that reacted with ammonia by the stoichiometric ratio, and then multiply by the molecular weight of ammonium oxalate to get the mass. Divide this by the mass of the sample and multiply by 100 to get 47.8% ammonium oxalate in the sample. For the last sample problem, zirconium reacts rather slowly with EDTA and must be determined using back titration. 10 ml of 0.0502 molar EDTA is added to a solution containing zirconium. Back titration of the excess EDTA requires 2.08 ml containing 0.054 molar of bismuth nitrate. Calculate the weight of zirconium in the solution. To solve this, again, we get the actual moles of EDTA reacted by getting the difference of the total moles of EDTA initially added and the moles of EDTA obtained from back titration. To get the total moles added, multiply the EDTA concentration by the volume used. To calculate the excess moles of EDTA from back titration reaction, first, get the moles of bismuth nitrate by multiplying its concentration and the volume used. Then, get the moles of EDTA using stoichiometric ratio. Remember that the multi-dentate EDTA forms a 1:1 complex with metals. Calculating, we get 0.3897 millimoles of EDTA reacted with zirconium. To get the mass of zirconium, simply use this stoichiometric equation. The millimoles of EDTA that reacted with zirconium is multiplied by the stoichiometric ratio, which is again 1:1 for EDTA metal complex. Then, convert to mass using the atomic weight of zirconium. We get 35.55 milligrams of zirconium in the sample. This ends Lecture 5A. Thank you for listening and see you in our synchronous session. Kill that bitch.